They didn't have printers that you could just use for like.
They weren't invented yet?
No, they did. They were, but like universities at the time weren't like all like student accounts to print. So I had to buy my own printer to print everything, and that was super expensive. And I was like, $200? I don't have $200. Yeah. So maybe this is an old man saying we had it hard in my day. It's possible that that's what's happening right now. I don't know. It's hard to say. But let's talk about sketching the root locus, because I know about this. I think. I'm going to pretend. Okay, so sketching the root locus. It is easy to get lost in the detailed rules. So there's a huge section in Nice about this, about how to sketch the root locus plot. So it's easy to get lost in the detailed rules of manual root locus construction. In the old days, old days, I'm already talking like that. Accurate root locus construction was critical. This is before my time. But now it is useful only for gaining intuition for how a given system will behave given its open loop transfer function, which is extremely useful for design. So it's like, oh, well, we could just use MATLAB to spool it out, but getting an intuition for how if you change something in the system, it would affect the controller design. That's the real reason to learn this root locus sketching technique. And it's really important. So if a detailed root locus is desired, we should use the computer tools of the next lecture, Factory. We will construct a procedure for sketching a root locus in the following rules that must hold true for every root locus. In what follows, phrases such as has locus are used to describe curves in the complex plane for which the root locus is defined. So where there's a solution for those closed loop poles for some value of the gain. That is, everywhere in the complex plane for which root locus is defined is said to have locus. Note that some of the following rules only apply for k greater than 0. So for positive gains. So like I said, if you want negative gain root locus, these rules don't all apply. There is a separate set of rules for negative gain ones you can find in the Nice textbook, but I don't think it's super useful to learn. This is the one that we use almost all the time. So rule 1, so you have to respect all these rules as you construct the root locus. The root locus must begin at open loop poles where k equals 0 and approach or end open loop zeros where k goes to infinity. So this was shown in lecture 5.1. Well, actually, this is lecture 5.1. It's the, actually, no. What was lecture 5.1? Whew. Lecture 5.1, the one we just did a minute ago. To follow from the form of the closed loop transfer function. So remember when we looked at the numerator denominator breakup and we said, oh, look, the closed loop poles start when k equals 0 at the open loop poles, and when k goes to infinity, it approaches the open loop zeros. That's what rule 1 says. So you got to start. You have your start point and your end point. The rule 1 tells you that. Rule 2 says that the number of branches of the root locus is equal to the number of closed loop poles. The number of closed loop poles is equal to the number of open loop poles, or zeros, whichever is greater. So you're going to essentially have these closed loop pole solutions. Whatever number of them that there are, that's how many branches of the root locus you're going to have. So their locations in the complex plane are going to sweep out a number of curves that is the number of closed loop poles. So there might be one for some given value of gain. Maybe these are your closed loop poles. That should be symmetric. Maybe those are your closed loop poles. And as you varied gain, they would move along these curves. So the number of curves in this closed loop, in this root locus, is equal to the number of closed loop poles. Okay. Great. The root locus is symmetric about the real axis. This is due to the fact that poles can leave the real axis only as conjugate pairs. This is something that we were familiar with from just looking at pole zero plots, right? Because poles and zeros only show up as complex conjugate pairs. So whenever you have one that's up here, you have to have one that is symmetric with it about the real axis. Okay, so that has to be true. So if you end up with a root locus where you've got like a pole, a closed loop pole right here, but you didn't have one that's down here, problem. Something went wrong somewhere. So nope. That would not happen. I can't just put an X because we're already using X's. And I can't use an O because O's are zeros. It's confusing. Okay, so this is rule 3. So the first 3 rules are pretty straightforward. Rule 4 and rule 5 are the last 2. They're the most involved, but they're not too bad. So on the real axis, there is locus wherever an odd number of roots, so poles or zeros, are on the real axis, to the right, and no locus elsewhere. So this is a bit hard to parse, but it's actually going to end up giving us a construction technique that's like super easy to follow. So like you just, I'm going to motivate it in this little bit, and then we will actually do some of these and we'll see that this is actually pretty easy to apply. But this is a consequence of the phase criterion, equation 5-6. Due to the fact that every off-axis pair of poles or zeros contributes no net angle, because their angles are equally opposite, only poles and zeros on the real axis contribute to the phase of a given point on the real axis. What did he just say? There's a lot happening there. But, so first I'm going to try to say that, okay, say you're looking at a pair of poles, complex conjugate pair of poles like this, okay? And we're trying to decide if there's locus on the real axis. So I'm going to use a different color for drawing the locus. I'll use green. So we're on this real axis. Say we're like at a point right here, and we want to know, does this point have locus, or is there a closed loop pole solution for some gain that allows me to have a closed loop pole here? And this is, and these poles here are the open loop sorry. So these would be actually on root locus themselves. So these would be closed loop poles, and we want to know if they contribute at all to a real axis pole location. And we're going to use the angle criterion to say that they have no effect, okay, because they show up in conjugate pairs. The angle this angle, I'll use a different color because it's confusing. So I'll use like gray. So the angle that goes from this point up this pole, I'll call this theta 1. And the angle that goes from here to here, I'll call this theta 2, but I'll draw it like this. Theta 2, that angle, they give you no net change. So if you add those two angles up, what happens? What do you get? So it's a little easier to see if you do this one as being, if you called this theta 2, I guess. The net angle contribution, if you add them together, is theta 1 minus theta 2. But they're equal in magnitude, right? So this is equal to 0. So anything that's off the real axis has no contribution. If you have something on the real axis, if you had something on the real axis, then that angle contributes 180 degrees. And it doesn't have to come up in it doesn't have to show up in a pair. Okay, so that's why anything on the axis can affect it, but anything off the axis cannot affect it. So this is going to let us do in the next set of construction rules, this method that we'll learn, we'll be able to use this to start at the real axis at the rightmost value, and just march along the left. Every time we hit a polar or 0 on the axis, we switch. Locus here, no locus. Locus, no locus. So that's I'm trying to motivate that, but I realized that the description was maybe a little too dense just in words. So next year, I'll try to come up with a graphical description that's a little bit better. Okay. So moving the point leftward, yeah. So pretty much this will help us construct where on the axis we have locus and where off the axis, and where on the axis we don't have locus. So on the real axis, this rule 4, will govern the whole thing. So it's pretty easy to use this one in the next section, and I'll explain how. So rule 5, missing poles and zeros are paired with infinite zeros and poles asymptotically. So an open loop transfer function with a different number of poles and zeros is said to have missing poles or zeros. So you know when you have a transfer function and it's like s plus 1 divided by s squared plus 2s plus 4, there's 1 0 and 2 poles, right? So we would say that this has a missing 0, okay? This is because the root locus begins at open loop poles and approaches open loop zeros. What about the systems with missing open loop poles or zeros? So like we say if this was our open loop transfer function, then it's got 2 poles, so we know that the closed loop transfer function when k equals 0 starts there, but it's supposed to end here, but there's only one of them. But we know we've got 2 poles that need to go to these zeros, so we have 1 0 that's missing. So we call it a missing 0. For these situations, the root locus begins or ends at what we call poles or zeros at infinity. So it's a term. So for a system with more poles than zeros, which is quite common, so we saw something like this a lot, right? This is pretty common to see. Some poles approach zeros at infinity asymptotically, okay? So that is the more common situation. Conversely, rarely, for a system with more zeros than poles, which is uncommon and is called a non-causal system. So this is something that we don't typically see. Some branches of the root locus begin asymptotically from zeros at infinity. Asymptotes originate at a single real axis intercept, sigma a, which can be shown to be related to the finite poles pi and zeros zj, with np and nz the number of poles and zeros as follows. So we've got, so I want to sketch this really quick. This is, this is a double pole pair at a real value of s minus 2, right? That's what the poles are. The 0 is at minus 1. It's right there. So one of these poles is going to have to go, so one of these poles is going to go to that 0 eventually, right? It's going to start there, it's going to go to the 0. Another one doesn't have a 0 to go to, so it has to go to a so-called 0 at infinity asymptotically. In this case, and I'll show you, I just made this up off the top of my head, and it's still super easy to solve. In this case, this is where one of them goes from this pole pair to the 0. The other one goes from this pole pair off to negative infinity, and that's the 0 at infinity. Okay? This asymptote that goes off to infinity is described by rays, these asymptote rays, that have some origin on the real axis, and then they have an angle. So actually, I don't want to rush this part. So we'll close for today. When we come back on Friday, I'll write out the location for the real axis intercepts and the asymptote angles, and then we'll learn how to do some construction. Okay? Whew. Okay, this was an action-packed day.